Good morning, everyone. Thank you for logging in. This is now officially number 22. So we are in episode number 22. Today we're going to be covering ion exchange resins, specifically cation versus anion. Let's make sure that everybody's given here a couple minutes to be logging in. Thanks again for taking the time to be here. My name is Alex Bassini with AWC Water Solutions out of Vancouver, Canada. I'm the business development manager here and the water treatment specialist. Today, we are joined by Allan Gray from Purelite. Allan, I don't know if your camera's on or not, or you can see me, but one of the nice things that we're doing today with ion exchange, I know we're all pretty familiar with the ion exchange principle. We are essentially changing one ion for another. And when it comes to softeners, we understand how they work. But the reason why we're going a little bit further or a little deeper into resins is simply understanding the principles of not only how they work, but how different resins will operate with different contaminants and some of the selective resins in there as well. So with that, just a quick background on what we've been doing, and you'll have a look at some of the webinars. This is what we've been doing now for the last couple months, so thank you, everybody. If you haven't seen any of these before, make sure that you can tune into the YouTube channel. You can kind of go there and review them. They're all pretty fun, or we think we're somewhat fun. Quick background on AWC. We've been around for 40 years. We design and manufacture water treatment plants. We have close to 600 plants now worldwide. We are based out of Vancouver, Canada, and we have projects that we've gone from South Africa to the North Pole, working a few in Latin America. Of course, all of North America as well. So, we kind of divide everything because it is modular. We divide everything into three. We've got our potable plants, wastewater plants, and also everything that is skid mounted. That's enough about us. I'm going to make sure to bring this over to Allan, and we're focusing again on ion exchange resins. So, Allan, go ahead, take it away.
Great, thanks, Alex. Appreciate that. I'm going to bring my screen up here now. You guys can all see that?
Yes.
Okay, so thanks for the introduction, Alex. Today, as Alex has mentioned, we're going to be talking about ion exchange, cation versus anion, some different types of resins, some different applications, and just a little bit on how the resins are made, and a little bit on the ion exchange process. So just first off, just a little bit about myself. I'm located actually in Airdrie, Alberta, and I cover Western Canada for Purelite. I'm a senior account manager for Western Canada. I have 25 plus years in the water treatment industry, worked in a variety of different marketplaces, wastewater, water treatment, done some project management, some service management, currently married, children, and the neck of the woods I live in, there's lots of ski hills around, so I'm an avid skier. So
sorry, Allan, can I just ask you to maybe zoom in on your screen? Maybe I'm just getting old, but it's a little harder to view on my end.
Sure, I want to make it full. Hang on.
And also the presentation mode, please. Yes.
Awesome.
Better? Okay, so just a little bit on Purelite, just because people on the call might on the webinar know who Purelite is. Some people might not be too familiar with Purelite, so I just got a couple slides just to kind of give you an idea of who we are. We're a privately owned company. We're based in the King of Prussia, which is just outside of Philadelphia. That's our world headquarters. We have a plant there in Philadelphia. We also have a plant in Romania and a plant in China. We are the only company out there, resin company, that's 100% focused of our resources on resin technologies. So we don't do membranes, we don't do carbon, we don't do chemicals. We strictly do ion exchange. We have all of our own in-house labs. We have our own R&D departments. We have our own applications department. So we pride ourselves on the fact that we're very much 100% focused on resin technologies. And just a little bit on the markets we cover, anything from hydrometallurgy all the way through to food and beverage, pharmaceutical, oil and gas, from the food we eat and the beverages we consume, the medications and power we use. It's improved through Purolite resin. So we touch with a large footprint across the globe with many different kinds of markets that we're into. So just a little bit on basic ions and water, and some of you might find this very basic, others might find it of interest, but I threw it up there because we're talking obviously about cations and anions and in the water stream and how we remove them with ion exchange. So your cations are your positively charged ions in water, and you can see up there the more common ones are iron, manganese, barium, strontium, calcium, magnesium, sodium, and so on, potassium, hydrogen. And then on the anion side, they're the negatively charged ions, and common ones there: bicarbonate, carbonate, chloride, sulfate, nitrate, hydroxide. And again, if you're wanting to remove cations, you have to use a cationic resin. If you want to remove anions, obviously you have to use anionic resin removal. So just a little bit on ion exchange, what it will exchange and what it won't exchange. So ion exchange will exchange dissolved ions. That's what we're removing from the water stream when we are using ion exchange. We're removing dissolved ions and we're exchanging one for the other. What it will also do is it will filter out particulate, dirt and rust. Just because the way those beads are formed and how they come together in the vessel, they will cause the size between them is quite small, so it will filter out down to about 5 microns. The reason why I put that up there is because it will filter it out, but your ion exchange unit is not there to be designed to remove dirt and rust. It will remove it if it's in the water stream, but what happens is it clogs up the beads, as you can imagine. So now these beads get clogged up with oil, with dust, rust, and dirt, and so on. And now it can't actually do its ion exchange. So you're going to start getting leakage, and you're going to have problems with your unit. So if you have particulates in the water stream, you want to make sure you filter those out prior to your ion exchange unit. What it won't exchange are things like dissolved gases, microorganisms, oils, or sugars. And if it's in a softening application, it won't lower your effluent TDS. So a little bit just on quickly here, just on give you a nice visual of an overview of what's going on when we're making this resin. So you start out with water, you add a monomer that gets mixed together, and then you add your copolymer. And when you add the copolymer into the vessel, it's basically taking droplets of oil and you drop them into a beaker of water. It'll automatically just form little beads, and so that's what happens. That's how these beads are formed. When the copolymer is added, they form these little beads. Standard beads are anywhere from 300 to 1200 micron in size, and there are approximately 7 million beads per liter of resin. So again, many beads in a vessel, and that's why you can get such good capacity for removing ions from your water stream. And then each bead itself has millions of sites on that bead to carry out the ion exchange. So on a cation unit, this is for cations, after that's done, the copolymer, after that's done, then what we do is called sulfonation. So we add sulfuric acid, and that's what becomes functionalized. That's what we refer to as a functionalized bead. By adding the sulfuric acid, it becomes a functionalized bead, and now it has that charge, and it can start to remove cations from the water. The average cation bead, as those numbers on the bottom, kind of mind-blowing, but 1.7472 times 10 to the power 17 reactive sites, and can hold up to 56 or almost 57 equivalents of cation per cubic foot. And as you do that, the bead does swell up a little bit when you add the acid. So this slide here is just on types of resin. We have gel and macroporous resins, the two common resins. So gel resin is kind of like what you think of when you look at a gel capsule. It's kind of more that color. It's a little squishy. It's not obviously as squishy as a gel capsule, but it's that kind of idea as a visual. It appears solid. It has moderate cross-linking. Cross-linking is the divinyl benzene that we use to basically kind of give the bead its kind of strength. So it's got moderate cross-linking, and it depends on diffusion throughout the bead to do the ion exchange. Whereas on the other side, you've got your macroporous. And just by looking at the picture there, you can kind of see why it's called a macroporous, because it's porous. It's more solid, and it's got these pores all the way through the bead itself. It has a higher cross-linking, so therefore it's stronger, can resist more oxidization and temperature, that kind of thing. And then the kinetics of how it works is more based on surface and getting to those pores as opposed to the gel. So then there's also what we call styrenic and acrylic, and this is just the way that they're made, with the chemicals are made, of polyacrylic or polystyrenic. The polystyrenic, you can see there's much more rigid and uniform there. On the polyacrylic, it's much more kind of open. You can see that there's more spaces in between the ion exchange sites. Acrylics can't handle as high temperature. Polystyrenics can, but polystyrenics are hydrophobic, as acrylics are hydrophilic. So just depending on, again, your application of what you're doing, what you're trying to remove from your water, will dictate which bead you would use. And these are both available in both cation and anion resins. So we're just going to talk a little bit about properties of resins. You'll see most of these bullet points here on a spec sheet, for example, one of our resins. If you get a resin analysis done, which we can do in-house in our lab in Philadelphia, you'll see a lot of these things mentioned on the resin report as well, analysis report as well. So moisture retention, because you saw in the previous slide, it's made with water. So there's a water component to the resin after it's made. There's a moisture content. Depending on the resin, could be 40, 45%, that's up to 50, or even higher depending on the resin, but that's called the moisture content or the moisture retention. Then there's things like capacity. You see that on a spec sheet. That's for how much capacity of ions it can remove, elements in the water it can remove per cubic foot, and that's usually measured in per cubic foot of resin. So you'll see that on a sheet. That's important for designing systems. Bead count, what kind of beads you have. They'll actually do a physical check under a microscope and give you a bead count. And then the screen size, the mesh, we'll talk about that in a minute. There's different sizes of beads available depending on, again, your application. Swelling ratios, these resin beads do swell and shrink upon regen and exhaustion. Depending on the bead, some will swell or shrink more than others. Color is not a specification. We'll put that up there because you can get different colored beads. Typically, our anions are more like opaque or white in color, and our cations are typically a little darker. That can be really helpful if you have a mixed bed unit and you're trying to separate it out within your vessel, and then you can see where your anion, your cation, and where the line is. You can get a good separation, but it doesn't make any difference to the performance of the resin what color it is. Just a little bit about bead size. So our standard beads are anywhere from 300 to 1200 micron, or what we refer to as Gaussian. And the picture at the top there on the right, you can see there's different sized beads. You visually can see there's some smaller ones and some bigger ones. Those are our standard bead size. Then we have a lineup of products that are called uniform particle size beads. They're typically 650 plus or minus 50 in that range. And you can see by the picture on the bottom right, much more uniform in size. All the void space between them is about the same. So uniform particle size would be used in like packed bed systems. It'd also be used in systems where if you're having DP issues, because a lot of those smaller beads can fill those voids and you can get more pressure drop across your bed. Whereas with the uniform particle size, all the void spaces are the same, so you get less pressure drop across the bed. So again, just depending on your system and your application. And the color, as you can see by the picture, it can be off-white or amber to black, and again, color is not a specification. So just a little bit on the ion exchange process. Now this one here, this picture we're talking about today is going to be for a water softener. We're using an example. So we have a cation resin, and you'll see the Na pluses on there. It's in the sodium form, and why we call it exchange is because you exchange something for something. So you're going to load on calcium magnesium onto the bead, and we're going to exchange it for sodium. So sodium becomes what we call the mobile ion. So that's why you see on the far left, you've got calcium magnesium coming on, and it'll load onto the bead, and then it'll knock off the sodium. Every time any ion exchange resin we deal with, you're always exchanging something for something. In a demineralizer, you'd be exchanging that for hydrogen. But for this example today, we're talking about a softener, so calcium magnesium, exchange it for sodium, and you'll see your anions there, your chlorides, sulfates, and so on. They come in, they're in the water coming in, but they just pass through because this is a cationic resin. So just a little bit on the process. In the service cycle, you've got your beads are in the sodium form, your bed's in the sodium form, your water comes in with your calcium magnesium. You also have some iron in there because it'll remove iron as well. Loading onto that bead and then bumping off the sodium and exchanging off sodium and for every calcium because it's divalent, you get 2 sodiums coming off. Kicks off the sodium, loads up the cations, calcium magnesium, so on, onto that bead. This is what we call kinetics. It happens in seconds, but it runs for hours. So what happens when those beads, those sites get so full of calcium magnesium, there's no more exchange to take place on those beads. What happens is it starts to become exhausted. So now you've got to regenerate your bed to get it back into that sodium form, so you can start from the beginning again, have a fresh bed. So on a regeneration, what's happening here? You've got your bottom picture there. You've got all your beads loaded up with calcium magnesium and iron. What we do is on a standard softener, we use sodium chloride. So we use salt brine solution at a very high concentration. So the salt brine solution comes in and it basically kind of overwhelms the system because there's so much at such a high concentration, and it basically comes in and it pushes off the calcium magnesiums, the irons, the cations out of the way and repels them off and reloads your bed. It's completed in minutes. This is just one more last look at it. We call it equilibrium shift. 10% brine concentration is what we typically recommend. Again, it's a very high concentration that just comes in and overwhelms that bead and basically pushes everything off and reloads it into the sodium form again, and now you're ready to start, put it back into service and start your cycle again. So just quickly on talking about just some different type of products. So this is this particular slide is talking about dealkalization, and you'll notice you can use either cation or anion for dealkalization. It has to be a weak acid cation, so that's our C104 plus or our shallow shell SSTC104. That's our weak acid cation. It removes hardness removed associated with alkalinity, so it actually will be doing dealkalization. And then we also have our anions, which is our E300 and so on. Those are what we call a chloride dealkalizer, so it would basically just use salt to regenerate, much like a softener, but because it's an anion resin, the chloride would load onto the bead and it would exchange your alkalinity for chlorides, but it would work exactly the same way as a softener, just on an anion form, removing your alkalinity. This slide's one to put up just to show you different. You can get ions, selective resins. You can't make a resin that's just going to remove one thing and nothing else. We can tailor them to have more affinity for one thing and the other thing. So it's going to remove nitrates better than another resin because it's more nitrate selective, for example. So you can see by this slide that we've got bromide, organics, nitrates, hexavalent chromium, petrochlorite, arsenic, uranium, barium, iron, and manganese. And you'll see anything that has an A on it, that's an anion resin, and then the stuff with C's on it is a cation. So again, there's a mixture of cations and anion resins here, depending on the application. If you're removing uranium, for example, you're going to be using an anion resin. If you're removing iron and manganese, you're going to be using a cation resin. So just wanted to give you an idea of a snapshot of different contaminants, and we have resins available for each one of those contaminants. So I just want to have a few slides here just to go into our SST resin, which is our premium resin that we have available. It's our SST resin, and the problem with standard resin is you'll see by the picture on the right there, we call that fisheye fouling. That's a cutaway. A bead was cut in half under a microscope, and you'll see the fouling in the middle of that resin bead. And most ion exchange systems are prone to fouling over time, and it's hard to elute impurities that accumulate in the core of each resin bead, and that's typically where these foulants want to accumulate, is in the core. of the resin bead, and then you start losing exchange capacity, and your resin starts to get fouled and needs to be cleaned or replaced. And then every time you do regeneration, that chemical is drawn into that center and it consumes some of that chemical as well inside these beads. And if you think about those other slides, how many beads are in a vessel, it can take up quite a bit of chemical. And then the physical polymer structure of the bead restricts the flow path, so there could be flow issues with fouling of standard resin. And the driving force is reduced, resulting in accumulation of foulants. So as those driving force through that bead reduced, the foulants start to come in there. So to get rid of that fouling, what's the solution? And that photo really illustrates the unregenerated core in the center of that bead. So the solution we come up with is this shallow shell, and the reason why it's called shallow shell is because all the ion exchange takes place on the outside diameter of the resin bead. So we add a core into the center of the bead. It's an inert core. So what that means is it's a strong core in the middle of that bead, but it's inert, so therefore there's no functionalization, so it's not going to draw in any of the ions into the center of that bead. Any that go in there will just pass through, but all the ion exchanges taking place before that on the outside of this bead. As you can see, everything's taking place on the outside, so nothing's getting into the inside to foul that bead. So not only is SST it's less fouling, it's also less chemical when you're doing a regen, because the fact that you're not drawing that chemical into the center of that resin bead, it's not consuming chemical in the middle anymore, it's just on the outside. And then the other benefit as well is we've seen huge reductions in fast rinse times on systems, and you put them into fast rinse on some of the larger systems out there. Because you think about it, fast rinse is the last step in your regen procedure to flush off the remainder of that chemical that might be left in there. And if it's all stuck in the middle of those tiny little beads, it takes a long time to flush that chemical out. Whereas if it's just on the outside, it flushes it off like really quickly. And we've seen as much as like 50% reduction in rinse down times, 25% reduction in chemical usage, and better quality water overall. So just a little bit of advantages: produces higher quality water, as I just mentioned, lower regeneration costs, higher capacity, better overall economics. It can be used in existing and new systems. It doesn't have to be a new. If you have,
Give me 10 minutes.
If you have C100, then you can put in this as well. And it's a proven technology. It's been around for a long time, and it's we have it at many different sites and saving customers a lot of money. And that's me. Appreciate the time, guys, and I'll pass it back over to Alex here.
Perfect. Thank you, Allan. Oh, there's a bit of an echo there. Okay, so now what we can do is we can open it up to some questions. If anybody has questions, we have some coming in on the chat. So with that, I know that Mike was answering that. Thank you very much, Mike. What I'll do is let me go ahead and share my screen on my end, and we can go through some of the questions. So the one that I had here coming in from Jim was in concerns to PFAS. You had mentioned that there were some selective resins. So the idea was, are there very specific selective resins that will go after PFAS?
And the answer is yes. Yes, we do. We have and we have our Purelite PFAS expert in Canada, Mike Weatherall, with us today as well. So, but yes, we do have a PFAS resin available. It's a proprietary product that we have. We've had it out for quite a while now, and we get great results with it. Much better than I know carbon's been used in PFAS removal, and our resin works much better. And there's actually a whole presentation that we've got on PFAS. I think Mike did one with you, Alex. It's probably recorded somewhere too. That you can look that one up as well.
Yes, that's right. We did. And so going back to the PFAS, just because I know some people might have not tuned into that one. That I think that went back to like episode number 5 or 6. Would that be a positively charged? Is that a cation or anion? Because I know it's a selective media that it's a sacrificial media, right? So it's not something you would typically regenerate.
It's an anion. It's a PFA 694E is our part number for that one.
Okay,
yeah.
So it is anion. Okay, all right. Jim, did you have another question? Okay, So while I'm going through, there's a couple more questions here, so we can open this up and we can go through the chat box here for a few minutes. So we have one here. Do you have a resin for aluminum removal?
Yes, we do. Aluminum is a little tricky because it's a pretty high foulant, and it would depend on what else is in the water stream. But we do have something that would work for aluminum removal. Yes.
I imagine with aluminum, you'd have competing ions and competing metals that would interfere with any kind of aluminum. Okay, so you'd have to pre-treat the water before you go after the aluminum. Is that?
And it depends on how much aluminum's in the water. Are we talking like a real high concentration or a low concentration? What other, like you said, what other competing ions are in the water as well? So it's not just cut and dry that anytime you have aluminum, it's this resin. It's going to be depending on a lot of other variants, and that's why when we are doing applications and stuff like that, we always ask for a complete water analysis of the water because that makes a big difference, and it'll dictate what resin we might have to use to make this work, or sometimes we might have to use multiple resins. It might not just be one. There might be two different kinds of resin, depending on the application.
Okay, we have another question here coming in through the chat box. So do you have experience with a CIP with a strong chemical solution in addition to the periodic regeneration with regenerant? So I'm guessing, if I'm going to reword that, you've got your standard regeneration, but would you regenerate it with a stronger acid or any other stronger chemicals?
I'm not sure if I understand the question 100%, but I mean, for strong acid cation, for example, you'd either regenerate with sodium brine, but that's for a softener, like we discussed. If you're doing a demineralization system, which means you want to remove all the ions, see in a softer system, you're removing the calcium magnesium primarily, your hardness, but you're exchanging for sodium. So therefore, your TDS overall coming out doesn't really change very much. Whether if you're in a system where you want to reduce the overall TDS, then you'd use what's called a demineralizer system. So you have a strong acid cation in a regenerating with acid. So you have to use either hydrochloric acid or sulfuric acid, are the two acids you would use, because then it basically puts it into the hydrogen form. So now you're taking out all the cations, including sodium, and you're exchanging for hydrogen. So therefore, your TDS comes way down. So I'm hoping I answered the question correctly, but the stronger regenerant would be sulfuric acid or hydrochloric acid for cations. And then on the anion side, on like a dealk system like I talked about, you just use straight brine, like salt, and it would just use the chloride portion. If you're putting it in a demineralized system, then you would use caustic to regenerate, to put it into the OH form.
Okay, so I got another couple questions, and yes, that does answer the question. I've got another one here from Jim. So it's asking about the SST media. I don't know that I was very familiar with the SST media, but it makes sense. What I like about it is now you're using less chemicals and even less water on the rinsing side. So, on the waterfront, I kind of like that. So their question was, can you confirm the ratio required for this resin on hardness versus iron or sodium versus hardness, iron, and manganese? Okay. Jim, thank you for the question. We might actually ask you to put that in an email because it might be a little longer answer than we're trying to put some of the time in here. And then the last question, we're going through these here, just trying to make sure that we stay within the 25 minutes. I've got one from Waleed that says, what are the typical process applications where resins are the ideal solution? So I guess if we're comparing resin to other applications.
It's a great question. Really, it's to do with a few factors, but if you want to generalize it, it would be your overall TDS in the water. If you get into applications where the TDS is really high, like you're 1,000 or 4,000 or 5,000 TDS of total dissolved solids in your water stream, it's not that the resin wouldn't remove what you're trying to remove, but it just overwhelms, it would exhaust the column so quickly that ion exchange doesn't become feasible, because it'll work, but you're burning through a column like every hour or two, and so it's like, okay, this is crazy. I'm regenerating all the time. It's just not efficient. If you have really high chlorides in the water, for example, that's going to really load up on a resin bed really quickly. So if you have a better way to go there, might be going with an RO system. But again, it's very application specific, because we do have like specialized resins that can handle higher TDS, and so depending on what's in there, but generally that's where you find, in a general sense, ion exchange might not be feasible because the overall TDS is too high and it just will exhaust the resin too quickly.
Well, thank you for that, Alan. So I want to send, I'm putting a quick link here in the chat box just so everybody gets it. That is, we can take a look at some of the videos that we have. We've covered a lot of some of these contaminants before. You can go through them. The video will be available by tomorrow afternoon, and everybody will be getting a link on that. So I want to thank you again for your time, Alan. If anybody wants to stick around, we can answer some more of those questions. We're just trying to be as mindful of everybody's time. I also want to remind you that we're no longer doing this every week. We're now doing it bi-weekly. So if you want to tune in 2 weeks, we're going to be doing a water treatment plant upgrades and retrofits. So this is not just taking a look at brand new plants, but I know that with some of the new incentives that are coming out and some of these grants, they're focusing a lot on something with the upgrades and retrofitting some existing plants for both water and wastewater applications. So thanks again, everybody, for coming. Thank you, Alan. And with that, I will see you in 2 weeks. Goodbye.
Great. Thanks, everybody. Appreciate it.